camera. Okay, so you should see, let me see if I can turn this off. Okay, when we talk about a prototype board, we're talking about a minimal system that allows me to test the channels on the RoboRio. And part of that is the ability to power up the RoboRio, which is the processor, which is over here in this corner. And we'll look at that a little bit more in detail later. First of all, we need a battery, a switch. We need the battery hooked up with the ground going straight to the battery and the switch going to the red connector or the positive connector on the power distribution panel. And there's two wires that come out from down here that power the RoboRio. And so with that minimal amount, you can actually load a program and make sure your program runs. And this other stuff over here in the corner, these white cubes are motor controllers. You may be able to see the word spark. And so each motor has its own individual drive. You can see the cables that are hooked up. And so the way this works is I've asked the team to build me a prototype board, and because the first thing I'm going to do, I'm going to turn my screen on. First thing I want to do is so we're recording now, is image the RoboRio. So when we first start off with, let's get out of here. When you install the FRC game utility, one of the icons that it installs is up here on this left. If you can see my screen and the mouse, a thing called RoboRio imaging tool. And if I turn on the RoboRio, I turn it on the switch, a bunch of lights start flashing, and ultimately you want to understand which light flashing where and what color means good versus what color means bad. We're not going to cover that right now, but I have the power applied. This cable is my USB cable, and it's hooked into my laptop. And now I'm going to run the RoboRio imaging tool up here on the top left. And as I launch it, it's a very powerful web search or network search vehicle, and it goes out on all my connections, whether it's Wi-Fi, internet, Cat5, USB, and it looks for any RoboRio that may be hooked up. In this case, it says there's a RoboRio that's programmed for Team 2411, and it's downloaded. I've already updated the firmware. It's got firmware from 2020 version 10, 2021 version 1, 2, and 3, and the one that's loaded here is 2010 version 10. So I want to pick out the latest, which is 2021 version 3, and I'm going to format, and I'm going to put in my new team number. So that maybe if it hasn't been formatted before, that it won't have this information. But I'm going to reformat, and now the idea is to load in my team number and set up the image of the game, which is what this zip file is all about. Now, this process takes about 5 minutes, so I'm going to jump back into my PowerPoint and come back to this after we talk about a few other things. All right, so that's what's going on now. To the question, and that I don't know if you guys can hear, I hear my USB going on and off in my headset, which means it's changing that I/O that's connected to my USB port. Okay. The question last week was, when will we see how to program the robot? Which I thought was an excellent question because it brought to mind, I really haven't explained the big picture of how the program fits into the robot design cycle. First of all, the team needs to get together and understand the rules of the contest, and that'll happen after kickoff, where they'll present a video and explain all the rules to us. And so you need to describe as a team what the rules of the contest are, and most importantly, how points are scored. And then you consider the physical parameters and capability of the robot that you want, and with the goal of scoring so many points. And sometimes scoring all the points is not necessarily a good thing because you may overextend your ability to design the robot. But in any case, it's the physical design that you're kind of looking for at that point. And part of this is to determine what features the operation needs to have. And so what actions are going to be automatically controlled, what actions require driver control, what sensors are needed, and what actuators are things that are going to move the robot around or allow it to do certain functions. And with that in mind, then the programmer really goes to work. And this goes to the point about building word problems. So in this case, let's just say the design team has decided they're going to build a robot that must pick up balls and hold them in a hopper, and they will have a ball in position sensor, and they want to use some rotors to pinch the ball and run it up the ramp to get into the hopper. So they're saying, yep, we will have some sort of a position, whether it's a limit switch or a photoelectric sensor that tells us the ball is in position. Then we need the program to start the motor and then push the robot up, push the ball up into the hopper. So it looks, and again, all this stuff up here is a team decision. Down here is where the programmer really starts to earn his keep. So let's say this is kind of the mechanical design we're looking on, and the function we're talking about is this one down here where the driver guides the robot so that a ball presents itself, and there's some sort of a switch that tells us the ball is in position. And we need to drive these motors at counterposing directions to be able to push it or kick it up the ramp. And so in the discussions that we've had, I've shown you how to drive because these are numerical signals now, to create a numeric signal that has a positive direction and a negative direction. And that's what we need to apply to these motors. So then the word problem that you should create, you as the programmer should create, is this. When the ball is in position, it is true. When that signal is true, because it's a Boolean signal off of the limit switch, and the driver presses the button on the joystick, then the motors will run for 2 seconds to push the ball up the ramp. And if that's what the physical designers want to happen, then this is the word problem that you need to solve as a programmer. Now, and we'll get into this a little bit more in next week, next class, but if this function you don't want to tax, if you don't want to burden the driver with this function, it could be included in an automated control, in which case the word problem would be when the ball is in position and the limit switch is true, then the motors will run for 2 seconds to push the ball up the ramp and then stop and wait for the next ball in position signal. And if that's what the team wants to do, then you need to design the system that'll make that happen. Anybody got any questions on that? Does that make sense?
I think it's pretty clear.
It's important for newbies. It's real important that you step up and start asking these questions. Don't wait for somebody to tell you this. You need to know what it is you're trying to do. So I encourage you, and asking questions is the best way to go. So I think it's a good sign that you've got people that are willing to step up and say, hey, I don't know what you're saying. Tell me again what's going on. Okay, so what we're doing tonight is I'm going to image the RoboRio. Before you run a program, after we've imaged it, that just means we can talk to it. The next thing we want to do is make sure that it's wired correctly. And so I sent out 2 Word documents that are what I call robot setup worksheets. And the idea is to have a list of every channel that's on the RoboRio, and then make sure that the wiring I/O, the way the robot is wired up, matches what you've agreed to. And so that device, see if I can find it. This list, this robot setup worksheet, is like the communication vehicle between the people doing the construction of the robot and the people programming the robot. So here we're showing the left motor has got two motors running, one on PWM0 and PWM1, and then PWM3 and PWM4. We're showing which is the right motor and which is the left motors and which ones are inverted. Because based upon the orientation, some or multiple motors need to be inverted. Here it's showing we have a servo on PWM5, a crane motor on PWM6. Now, and so this has all been determined by the people doing the wiring. And we'll get into some of this other, but this is the way that the joystick is set up. And so there's an agreement that we want to have tank drive, and so we're going to need to have the x-axis, the y-axis of two joysticks come out and be available for the drive mechanism. So this is a typical setup worksheet after the design has been done. And the idea is if you're going to change something in the physical design, the programmer needs to know what you changed, and we both agree to make a change to the setup worksheet. Okay, now, so what I'm doing tonight is I've got a setup worksheet for this particular robot, and I want to make sure that the wiring matches. We've got PWM0 set up to drive the right motors, PWM2 for the servo, PWM6 for the left motors. We got a gyro on the SPI port, and I think that's all I've got. Okay, so with that in mind, let's go see how our imaging tool is working out. Okay, so it's completed the image, and it says it was successful. The IP address is 172.22. The host name is my team number, and it says you must deploy code to use the robot. It's like, okay, fair enough. And when I click OK, what it's telling me is it's programmed the image in the RoboRio that allows me to communicate with the RoboRio from the driver station. So now that I've recognized that the 3243 is the team number that's been programmed into it, and we're with our latest version of the field image or the game image, I'm going to close this. I'm going to go out and open my driver station. Now, if you recall, and so the thing that we haven't done in all of the classes we've done so far is build the code. We played with it in the simulator, but we haven't really built it. So now I've got a dashboard and a driver station. Now, the fact that I have this set up for this team number allows me to see that there's communications with the RoboRio. If I have a different team number in here, it's not going to like it because the communication system is not set up to recognize this other number. And so this is what keeps us different from anybody else on the field, and it's important to stay on track. Now you'll notice it gives us the status of the battery. The battery is a 12-volt battery, and you don't want it to drop much below 11.5 as you're running, so you want to keep charged up batteries available. Over here on my tab, I'm showing that I have a robot with this IP address. This ENet is available, but I don't have anything hooked up because I'm connected to my communications through the USB drive. And then if I go to USB, I can see I have a joystick, and it's hooked up to display up here at the top on the dashboard. And the robot doesn't have a camera, so we're not going to worry about that. Now, the next thing I want to do is do my wire check with my robot setup worksheet. And to do that, I want to use the examples that they've given us in LabVIEW. Let's go up and open LabVIEW. Okay, so when I say we're gonna set up, check the wiring, I'm gonna use the motor control example and verify that the right motor is connected to PWM0. So the way you do that is come down here to Support, click on Installed FRC Examples, and it brings up this little display here. And what we're looking at first of all is robot and motor examples, and I want to go with the plain motor control. Now, with my teams, every time we've turned the robot off for more than an hour, more than 2 hours, let's say, like overnight, or we've transported it, I insist that when they first turn it on, they go through every channel and make sure nothing has changed since we last turned it on, because we don't want to run program where the wiring is different than what we expected. So if I double click on this motor control example, it opens up an example for me that looks surprisingly like a robot project that we've been using, except there's not the FRC framework. There's just a VI, and again, they're showing us an example of how both to hook up the motor. So this is what the robo reel looks like. And all the channels along the right-hand side, if we're facing it, are labeled PWM or pulse width modulated. All the channels on the left side are digital I/O or DIO. There's 4 relay channels down here at the bottom, and there's 4 analog channels. Now, this is a motor controller, and they show us the colored wires on a PWM cable and how the orientation should be. So right now I'm going to test PWM 0. If I look down at my motor control system, I don't know if you guys can see it, but I can look over here. I need my flashlight because everything is a little bit dark. I want to verify that I have a all right, so there's PWM 0 here, and the white cable or the white wire is to the inside, which is the way my example says. Now, I'm going to run it. Before I do that, I'm going to show you what the block diagram looks like. And the reason we want to see the block diagram, this is how we would hook it up to run it. This is how the program is running right now, but this is what we need to reproduce when we get into our own program. So I'm going to run this with the arrow. It's going to show me that it's deploying it. It has to check for the conflicts in the communication link, and then it dumps the code. Now, right now, it's running the code as it loads this code into DRAM in the RoboRio. And so we're running it both in my laptop and in the RoboRio, and that's why we can use probes when we want to look at the block diagram. Okay, so it's loaded it in. Now we're registering that we have robot code. And you notice we need to have the driver station running and teleop enabled. All right, so again, this is a dangerous machine, and especially when it's hooked up to my laptop with a USB cable, I don't want it to get out of control. So before I turn anything on, before I enable anything, I want eyes on the robot, and I want to make sure there's nothing touching the wheels or any wires or going to be anything that's going to be moving. So right now things look pretty clean. Now, another thing to remember is emergency stop is a space bar on your computer. So the first time I turn on a robot or have any of my students turn on a robot, I have one sitting with their finger over the space bar, and if anything goes wrong, shut it down. Okay, so with that said, let's go ahead and enable it. We have a zero signal. Now I want to increase this just a small amount. So 0.1, nothing is happening. 0.2, can you guys see that moving? All right, so that's the motor over here. And if this is the front of my robot where the RoboRio is, then this is running backwards. In other words, this is trying to move the robot backwards. And I make a note on my setup worksheet that I'm giving it a positive signal, so that motor itself is running the right direction according to a joystick. And if I put a negative signal, now the motor's running forward. Now I can look at, you'll notice my motor controller flashing lights changed from green to red. So all in all, I'd say I've satisfied the wiring check. The PWM right drive motor is correct and it doesn't need to be inverted. Now, right now I would not necessarily run it up to speed, but if once I was happy with everything, I would set that puppy off and make sure it ran. Okay, so I stop, the code's gone, it's no longer in RAM, and if I can't run anything with my RoboRio, now I want to go to the next channel. Right, so right now, this is non-inverted as it's sitting in the robot. The right channel does not have to be inverted. And again, I make these notes as I'm doing it. Now my left channel is on PWM6. So let's look at PWM6. Now, if anybody's got questions, by all means, stop and ask me, and let me show you whatever I'm trying to show you. So I'm looking over here at PWM6. It looks like it is PWM6. And you can't see it, but there's actually a Y PWM cable where I'm driving two controllers with one PWM cable. And the reason is we're driving two motors off of one channel. All right, so let's go ahead and, now that I've changed the channel on my example, I can run it. We've got good code. I'm going to enable it. Again, I'm checking to make sure there's no wires or nothing touching the motors or the belt drive over here on the right side. And I want to start very slow. Okay, with a positive signal, the motors are driving such that they would push the robot forward. So that's the opposite signal that I would get from my joystick. So this tells me that my channel PWM6 in my program needs to make sure it's inverted. And if I go negative, motor goes backwards. I don't know if you can see that, but you can also see there's red flashing lights from my motor control. So at this point, I'm happy. I can probably make a lot of noise. Okay, so I'm happy with my motor connections. Now I need to make sure that I'm making a note, again, for my program to make sure that it is inverted for PWM6. Okay, I've also got a servo on PWM2, so let's go find the servo example. So I'm going to close this out. Go back. My example is this little magnifying glass down here in the taskbar. I'm going to look for the servo BI. And it's exactly the same type. It shows me how to hook up a servo to my PWM channels. It shows the white wire to the inside. So my PWM channel is this little puppy right here. I just have it sitting up on the edge of the robot. And it is on channel 2. So it's 0, 1, 2 as far as the PWM channels. And my white wire indeed goes to the inside of the RoboRio. Now, if you recall, the servo well, let's just see how it runs. Part of this is understanding how the device works, and it follows the angle that I give it. And I want to make sure that I put a little sticky note on the wheel so we can see if it's turning. Okay. Now again, we need to activate it because and then so I'm not seeing anything change. Ah, I got a PWM7. Nice going, Jim. So let's stop. We want a PWM6. No, 2. Sorry about that. Here I was saying bad things about my wiring team, and it was me. PWM2. And again, I verified that there's something on PWM2. Looks like it's a servo. All right, so we got the code running. Let's enable it. You guys see the little sticky note changing directions? Now this is what's used in a remote control airplane system for the ailerons. So it's got some fairly decent torque on it. Can you see it change? Oh, it's over here on the bottom right. Okay, so I haven't verified the angle. I'm not too worried about that, but it does follow the commands to increase and change the angle. Okay, so the only thing left in my setup worksheet, so I'd make myself a note that the servo seems to work okay. The only thing left is my gyro, which is plugged into the robo Rio itself. So I'm going to call up the gyro angle, the gyro example. Now, again, I strongly advise testing all your I/O channels before you run the code for a number of reasons. One, it's good practice, and two, there will be a time when things fall apart, stop working, and you're going to be in the middle of a contest, and there's going to be all kind of noises going on, and people looking at you to make sure you're going to get it to work, and you need to have something to keep your head together. And being able to run these examples and know them like the back of your hand will be extremely useful in troubleshooting what's going on in the robot. So don't be afraid to practice these channel checks every chance you get. Okay, so again, this is a gyro example. It's actually plugged into the robo Rio itself, and this location is known as the SPI, or serial peripheral interface. So it's the onboard C50. We're going to run it. Now it's set up for a sample rate of 100 hertz or 1000 hertz. So I'm going to, by default, just take their word for it. Seems like it's running pretty good. Now, if I had a different type of gyro that had a cable on it, I could pick the gyro up and move it independently of my cable. So I can see that my device has been recognized. If I go to the block diagram, it's showing me, okay, on one of the outputs from the get angle, oh, it's actually from the pipe coming from the gyro, is the recognition that it's been found, and so it's showing me a positive signal. It found it when it booted up, but it's not finding it now because it's not executing. We're inside this loop. So what I was trying to say is, to see if the gyro works, I have to move the whole robot. So unfortunately, I have it on a box that I can kind of scoot around. So my gyro works. Does my reset work? It works. Anybody impressed yet?
I'm impressed.
Good. And I strongly suggest that students go through this every time you turn the robot on for the day, for the night, for whatever your meeting session. Okay, so now we verified that our wiring team did a good job. Now I'm ready to load the code and try to run my code. So let's go back to I wrote this down somewhere. And there's a couple things I want to do. First of all, I want to open up the dashboard. I actually wrote these down. So 2031 dash. We're going to build and store a dashboard that reads the servo right here. Okay, do you remember when we were playing with the dashboard in the simulator? We just ran it in real time. With this, I want to build it and then be able to reuse it when I launch the driver station. So if you'll notice, the front panel of the dashboard looks like the dashboard. If we go to the block diagram, I've read, I will, when we get to the program, I will write the value of the gyro into the network table, and in the dashboard, I want to read that value, and I would connect it to the display I need for this spelling and case for this channel name to match what I use in the program itself. Now, we don't have a camera, so we're not going to worry about the image right now. So now I'm going to save this and build it. And to do that, I need to look at my project. So I'm going to build. So just right click and build. Takes it a couple minutes. So, okay, lock file can be read only if you shared others. Let's say it's going to be okay. Now, with that in mind, I'm going to close this one. This is the one it loaded originally. And we're going to have to check to see if it comes back. So I'm going to keep this handy. Next thing I want to do is open up a program that I've already written in the robot project. So let's go to my getting started page. And all I'm doing here is I'm finding the program that I already constructed and showing you what I've done to make sure I match my 3021. Let's hope this is it. Nope, that's not. Okay. Okay, again, I need to have my motors lined up with the channels that we're using in the setup worksheet. So here, this is not the one I already did. Let's give me a chance here. Talk among yourselves. I'll be right back. Any questions about the setup worksheet? Everybody understand what we were doing?
Yep.
I'm okay with you there.
Okay. So let me catch up here. I've actually already got one set up with the gyro is the main thing I'm keying on. Yeah. So I've already set my gyro up with the SPI on board as the channel. I'm using the default name. You can see I've got the left motor is PWM. So my right motor is PWM0. So I need to change this because of what I tested, right? And then the left motor is PWM6 needs to be inverted. So left motor is inverted and the right motor is not. Everybody follow that? I'm showing a Victor, and in fact it should be a Spark. So need to make sure we're matching our I want to make sure it's not a Spark Max. It's not. Okay, so I got my channel set up for a motor. The right motor is PWM0, the left is PWM6, and the left is inverted. My gyro is set up. My servo is PWM2, and what I've done now here we go with IntelliOp. If you guys recall last week, what I do is disable everything that's IntelliOp with the exception. So I disable all the code that exists, except I write the program name to the dashboard. And so one, it tells me that we did get into IntelliOp, and two, it tells me what the name of my program is that I've loaded into the RoboRio. And then finally, I put everything in the periodic task. And what that means is in the top loop, I call it loop A, sensors and joystick. Here I've unbundled the joystick from the pipe because I know it's joystick 0 has been put into the pipe. And I use the get value icon. I take the array for the joysticks and I use joystick x-axis and joystick y-axis, and I save it or I load it into robot global data. Then I also write the joystick axis to the dashboard with this label, which was used in IntelliOp. Likewise for buttons, we index it. I'm going to use button A to, I think, reset the gyro. Excuse me, button B. It's going to be used to reset the gyro. And then button A is going to be, it's going to control, I don't even remember what I did. It's going to control the servo. So when button A is false, the servo is going to indicate 25 degrees. When button A is true, it's going to indicate or move to 120 degrees. I've saved the angle for the servo to robot global data. And I've set up the switch in loop B. The switch is set up in a case structure controlled by whether or not we're in robot mode equal to autonomous enabled. If it's not, then the joystick controls my RK drive. If we are in autonomous enabled, then my auto left and auto right are controlled from robot global data. In robot global data, I've got my joysticks, x-axis and y-axis, buttons A and button B. I've got the raw gyro data and the gyro display coming from my gyro output. You'll notice it's on a 360 range for the display, and when it's raw, it's going to be something different. We'll look at that when we run it. And then, even though under my auto controls I have auto left and auto drive at 0, I want to make sure I don't accidentally have any values set for that. So back in begin, I set up and set those values to 0 right here. Likewise, they always set up autonomous disabled for robot mode, so nothing can move when you first enable the robot. Any questions about any of that? Okay, so we're going to run the program for the first time and see if it's running. Let's open up robot main. And I'm going to go back and see if I can tell if my go back to default and then see if my LabVIEW data version is going to come up for me. Okay, I'm going to run the code on the robot. We have communications, we have good voltage, and it's doing its thing. Anybody have
Do
any
you have
questions?
to redeploy that code every time?
Well, I do until I flash it. I mean, I haven't even debugged it. So first I'm going to debug it. And then once I'm happy with it, I'll load it into the flash. And then the answer is no, I don't have to. When it boots up, it'll have this code in it. That's the last.
Okay.
That's what we're doing. And that's the step we haven't covered before. So right now I'm just running it similar to the way we were running the simulator. And I want to make sure that my controls work. And if I've got the right dashboard, my gyro indicates. Now, this came up with an error that says, okay, the gyro is having an issue because we're overwriting the depth of FIFO. So I'm going to go back and talk about this for a second. I'm going to stop it with finish. Turns out one of the neat technologies that's included in the RoboRio is a technology called field programmable gate arrays. And as we load code in there, it reconfigures the electronics inside the RoboRio based upon the characteristics of whatever device we have used. And when I set up the gyro, I used a default value of 2000, and what that error message was is that the RAM, or the FIFO, first in, first out memory that's allocated to the gyro function isn't that large. So we're going to go back to 1000 because that's what they used in the example, and see if we can run that without getting that error. The
Little
technology.
details like that's what scares me.
Well,
We'll run into things.
but see, that's what's going on here, is that it gives you clues, and you just have to do a little bit of research. And you know, I should have stayed with what was in the example. I didn't. I took the default, and I made a mistake. But it's the reason for the details is there's some pretty cool technology that most of the public isn't aware of. Okay, so let me see if I existed here. WPI set value Okay, that one I'm not familiar with, so I'm not going to think anything's wrong yet. Okay, now here's another thing. Before I run the code, whoops, before I run the code, I want to verify all my controls work. So until I've enabled it, nothing's going to drive, but my robot global data is indicating all my signals. So the joysticks work, the gyro is drifting, which isn't hurting my feelings too much. The buttons work, and I've got 0 for auto drive. So all of my controls are working as far as the program is concerned. So now I'm ready to go to teleop, enable. Now, the other thing that you'll notice, even before I go to enable, is I should have, you notice right here on the dashboard, I've got my joystick indicating, and these are the motor control signals. So if I go forward, I've got the left and right, one going a different direction or a different signal than the other. And because it looks correct, because the right side is negative, which we would make it go forward, and the left side is inverted. So again, it looks like things are in good shape. So I'm going to enable it. We got my network connection. I'm going to go forward a little bit on the arcade drive. So pushing the joystick forward, I get both sides going forward. Pulling it backwards, it goes backwards. If I go at an angle, one side goes forward and the other side goes backward. See what I'm talking about, Leo, as far as the signals from the joystick driving each side. So this is arcade drive. So it computes based upon what the joystick is doing, what signal it needs to send to the left and right side. Now, one of my other signals was the servo. So with A button, we're controlling the servo. You guys can see that down here in the corner. So apparently this is 25 degrees, and that's 100 and something. And I can look at my dashboard and verify what that is. So my servo angle is 25 when it's false, 120 when it's true. And so the way I got that, Leo, was when I was talking to the design team, they said, okay, when I push button A, I want the servo to be at 125 degrees. And when I don't push button A, I want it to be at 25. And I said, yes, sir, that's what we'll do. Okay, now, then, because what we're going to do is deploy this into the flash, we won't be able to use probes. Right now we can use probes because we're still running the code in the laptop. When we deploy it into the RoboRio, we won't be able to see it, but because we're writing the variables on the robot global data into the dashboard, we can see them change here. And this is what we would use to debug it or verify what's going wrong.
When you talk about probes, you mean looking on the main global, the robot global data?
No.
Those are the probes you're talking about?
No, I'm talking about the ones that we put in. If we go to the block diagram, we can look at the probe right here. And so this tells me all the buttons that are coming off of that joystick. And if I push a button, it tells me what's happened real time. And I can probe any signal line in the system. So let's say I want to look at my angle.
Yeah, I don't remember us talking about that before. So what are you doing to get the probe? Are you holding down a special key?
Nope, you just left click.
Or you just hovering over it?
See, it has a little P on it whenever I So let's look at this. Right now, I'm using the joystick to drive the motors, so I can put a P probe there. Now see, here's your dead zone. See, based upon friction and inertia, there's a built-in dead zone in the motor controls, right?
Okay.
Right. So we saw it in the simulator. It's not necessary to do it in the robot itself. But yeah, we've talked about these probes. You might want to go back and see first or second lesson. But okay, so again, the purpose of it is to allow me to debug. If things weren't going right, I could literally track my signal through a logic chain and figure out where it was going wrong. Fair enough?
So once you flash the code, you won't be able to do that anymore.
With the probe, right. And so that's why we write
Okay.
it to the variable list, and we can see the same thing. We can have what are effectively probes by where we've written out that value to this list of variables. Now, I want to see if I'm indicating, I'm going to twist this around and see if my gyro's hooked up. Nope, we didn't get the gyro. Okay, we'll fix that in a minute. All right, so right now I'm happy with the robot code. Everybody agree with me that we're solving our problems? I'm going to finish it, finish robot main, save the program. The little asterisk means it hasn't been saved. So we're going to save all. Now I'm going to go back to the build specifications, and I'm going to right click and save it as a file that can be loaded into RoboRio. So I'm going to start a new one. I can build any number of different real-time applications, and that's what's called when I load it into the RoboRio Flash. So let's say a new one. Let's call it Jim's First. And I might have 2 or 3 that I want to try and compare or whatever. And then I go to Source, and I want to include my robot main as my startup VI. And then I build this project. Now again, that's why I write the program name. Yeah, write the program name into my variable list, because once I put this in Flash, I may forget where I got it, where even I named it. There's reasons you need to keep track of what worked and what didn't work as you're kind of trying different things. So yeah, once we flash this, it'll actually go into the flash memory of the RoboRio, and it'll be there when we boot it up. You notice when we boot it up this time, there's not any code in the robot. And so there won't be any until we run another program or we reflash it so it can boot up itself.
If there's code in there and you image the RoboRio, does that wipe out all code that might be in there?
Yes. You don't want to image that often, but it's possible to have dangling code. And that's I've seen one of the hazards of not closing all the I/O channels in Finish. So if you run code that has open program running, you may, in a worst case situation, you may have to go back and re-image. It's something you don't have to do that often, though. Okay, so it built it. It says it's in the build folder for LabVIEW builds 2021 servo target. Now what I'm going to do is I'm going to take that and I'm going to run as startup. So I'm going to set it to boot up, and it's going to deploy it into RoboRio. And so bang, it's done. And there it is. Now, if I come back here to my setup, I can reboot the RoboRio from here. You can see it turns off the communications. If you watch it, the lights start going off on the RoboRio itself, not necessarily on the I/O channels. And then as it comes back online, it will reboot up that code that we just had in it.
What's the difference between reboot RoboRio and restart robot code?
Restarting code is a warm boot, and rebooting is a cold boot. It turns off the power and recycles to the RoboRio. All right, so now we've got the robot code. Now if we run it, so I can close this program. It doesn't need it now. Go ahead and save it. Now you can see I've got my communications. Now I cannot show my robot global data now because it's inside the program. So that's where my variables show up. And the signal changes, but it doesn't change the servo until I activate or enable the program. Okay. Any questions? So I've
Now,
got
you didn't do anything with the CAN bus. Are you going to do that next time?
there's nothing on here that has CAN bus. CAN bus is an excellent way to go if you're going to use a lot of motors. It's a little bit, it takes some finesse to use it. So the answer is no. I've not been that successful with CAN bus for a number of reasons. You got to use a different, you have to set up the addresses in each individual. There's a CAN bus control system that you have to set up the addresses in each of the controllers. So no, I'm not a CAN bus kind of guy.
Okay.
Now along that line, if you'll notice on that RoboRio that the setup worksheet for the BunnyBot, there were a lot more than just 8 or 9 PWM channels. There's an extended footprint you can buy as a socket for $100 that gives you another 10 motor channel PWM channels that can be used without any additional hardware. Okay, so we've done everything except for build the. Let's kind of look at that. When it saved my program, when I built the program, it saves it under LabVIEW data, builds. And so here's the dashboard that we were talking about, the link for the dashboard when we launch it. This is the executable that is launched when we open the driver station. Here's there's the servo gyro. And there's Jim's first. And this is what the code that gets booted up whenever we deploy the code into the RoboRio. Okay, have we overwhelmed anybody? Any questions? So I was planning on, Doug, I was planning on doing state machines on Thursday. Any other
Okay.
requests? Can't do much with CAN. Um, I can't, but it's certainly something to look into. Anybody
Okay.
else have any questions
So
about stuff?
Yeah,
you
Jim,
talked about gyro raw, the raw gyro as opposed to the other gyro. What's that?
Oh,
What's the difference?
it's so if you look at the signal, let's do that. Now, another question you asked was if you run another program now. So even though I've closed it out, let me see. I don't think I put it in my put it in my code, but not into the variable list. The difference is the display. If we look at the signal coming straight off the we look at the signal coming straight out of the gyro, it goes from minus 180 to plus 180. And that's, as far as I'm concerned, that's easier to use when I'm looking at it in autonomous. But when I want to display it on the dashboard, the signal, the display that they show goes from 0 to 360. So there's
Oh,
conversion involved.
okay, that's all. You just converted it into more user-friendly numbers.
Yeah. And so
Oh, okay.
I like using the raw data for autonomous because I don't have to worry about things being greater than 360 or greater than 180. It's always going to be less than 180. And I just take the absolute value and I know if I'm turning right or left with the motor control. So, um, so we were, so let me just run this and show you. So now that we've got this open, even though I've got the same program is what's booted up, I can rerun this program and be able to place my probes and look at it accordingly. So watch this. So we already have a real-time image running, and I'm going to say, okay, run this one. And it'll say, are you sure you know what you're doing? Because we already got something going. See, it says it's already running in real time. Are you sure you want to do it? So I say, okay. Now again, this doesn't get rid of it. This just runs it into RAM. And that's why I might want to run, say, something with different servo settings in it and see how it reacts. Does that make sense?
Yeah.
So yeah, it's good to have some basic code in there just so that you can verify your program's running or working. But I'd strongly recommend going through the robot setup worksheet using the examples and getting good at it so that you won't be rattled when something stops working in the middle of a contest. So now I can look at my robot global data. And I think I have gyro and raw gyro. So right now, if it's near zero, it's zero, but if it's near zero here, it can be a very large number, right? And as it turns, So if I go right, it'll be the correct number. If I go left, it'll be a negative number, but it gets converted by this little setup right here.
Okay, that makes sense.
Yeah. It's surprising how easy it is to deal with that and still have a neat display on the driver's station. Was there another question?
Yeah, Jim, this is Steve.
Hi.
I have a question. So this network table is what shares data between your program and your driver's station, or sorry, the dashboard, is that right?
Correct.
And did we ever talk about how that gets set up and how we know what's in there and what's not?
Well, it's already there. It exists. It's part of the framework. And so when you use the read and write icons from the dashboard, let me stop this program. Here's another point. If I stop this, I don't have code in my RoboRio right now. If I reboot it, oops, if I restart the code, then it'll start the code from Flash, which is what we had loaded. Okay, so Steve, back to your question. If I come in here and right click and go to my WPI Robotics library, there's the NT dashboard, network tables dashboard. These are the two primary ones that I use. So read pulls the information down from the table and write puts it into the table. So if I want to store anything, I can store a Boolean, a numeric, a string, or arrays based upon what's coming out of here, where it's being delivered. So coming out of the joystick, it has a network, an array of numeric values. Coming out of the buttons pipe, there's an array of Boolean values. That's what displays in the variables list as we run a program. So here's all my axis values. Here's all my button values, and you'll see them change as I change the button. That answer your question? So if you use, that's all right. That answers your question.
There.
Yeah.
If you were to start a new program from scratch, would there already be stuff in this network table, or it's just blank and it's whatever you write into it?
Yeah, it gets reset when we turn the code off. We stop the program.
Not the values.
I should say that.
The variables.
No, if a program's not running, this channel doesn't exist. Let's kind of prove that to ourselves. If I come back here and look at my dashboard, here's my variables. If I stop this code, well, so this is booted up there. So it's just kind of, so you see it go away. The channel still exists. But I think it's because it was set up. This will change when I enable. No, I don't know when this gets erased. It's not active now, but it was stored there and we didn't erase it when we turned the code off. So apparently this is in non-volatile memory. Let's try that. Yeah, we rebooted the Robo Rio and we still had these values displayed. So as a network table, which apparently is maintained by the dashboard, that makes more sense, right?
Mm-hmm.
So I'm not sure what difference that makes.
All those variable names that are in there,
Yeah,
that's something that you chose. You
all
had to
this
choose all those
stuff.
variable names?
Yeah, all this stuff up here are default values from the dashboard itself. So if you remember, we talked about these and these. So they're built part of the dashboard. And so if we come back here and look, so here's our two buttons that I pressed, and here's the two sliders that so they're part of the dashboard. So that kind of tells you where that array is maintained. Those names are maintained. Any other questions? Okay, so I think that the only thing that I haven't covered is state machines. And again, I use, there's more elegant state machines if you look at the LabVIEW National Instruments tutorials. I go with something that's similar to my flat sequence autonomous, which is a methodology where you can more easily see what each state does, and it gives you a clue as to where you have problems versus looking at an array of variables. So I'll cover that next week, next Thursday, and if there's any questions, we can wrap it up at the same time. Doug or Steve, do you have any other things you want to see us cover?
No, I think that'll do it for me.
Nothing that I can think of now.
Okay, well, yeah, it's a shame not to have a more complicated robot, but yeah, we could show the robot responding to the gyro in autonomous and hopefully put a little bit more clarity on how that works as well. So we'll do a state machine and then autonomous next Thursday. Okay, that's all I got. Anybody with any questions is welcome to email me, and I'll talk to you Thursday night.
All right, thank you very much, Jim.
So long.
Goodbye.
Goodbye.